journey with me, Ryan. In this next section, we're going to have a discussion around IPv4. We're going to start with Classful Networking and addressing. For those who don't know, you can contact me here on YouTube, on LinkedIn, or Twitter. So first, we need to have a discussion around what is IPv4. And I've got a little question there. Can you remember which layer it works at? In the previous videos, we've discussed the TCP/IP and the OSI model, and we said IP works at a particular layer in that model. If you're unsure what layer it is, go back and watch those videos. But those of you that do know would know that it actually operates at layer 3 of the OSI model. Now, the way we're going to structure the next couple of videos, IPv4, subnetting, and so forth is probably, in my opinion, one of the most difficult topics to get your head around if you're a beginner in networking, and it's also one of those crucial topics because it helps put together everything moving forward. So we're going to cut this up into a few videos and explore each video in depth, starting with this one, which is going to be primarily focusing on classful and a binary. In our next couple of videos, we'll talk about fixed length subnet mask and variable length subnet mask and subnetting as a whole, and then we're going to go into the CIDR and classless, and then we're going to end with some miscellaneous. So we're going to talk about reserved IP addressing, unicast, multicast, and broadcast, and how they work with IP. And then we'll also touch base on things like the API/IPA, loopback addresses. So before we get stuck into understanding classful and binary, I want to actually take a step back and ask ourselves, what is IPv4? Okay, so what do we need to know about IPv4 moving forward? The first thing is it's a 32-bit addressing system. So you can see here that when we mean 32-bit addressing system, we mean 32s, 1s and 0s. So this here represents an IP address in binary format. However, we normally display them in what we refer to as dotted decimal, which is displayed in this format. Now, the 32 bits are split into what's called 4 octets. So you can see here each dot breaks up the IP address into a single octet. So there's 1, 2, 3, 4 octets in total. Within each octet there are 8 bits. 8 bits equal 1 byte. So that's 1 byte here, and another byte, another byte, another byte. So that's 4 bytes in total. And then 4 times 8 is essentially 32. So we know there's 32 bits. But instead of calling them bytes, we tend to refer to them as octets. So there are 4 octets, each octet considering 8 bits. 4 times 8 is 32. So in total, there's 32 bits. It's represented with binary as far as our PC is concerned, but we as humans see it and translate it into a dotted decimal format. Okay, so moving on. Each byte is 8 bits. We call it an octet. We know this. It can be anything from 0 to 255. So essentially this means that if we think about our IP addressing, it could be anything from 0.0.0.0 up to 255, 255, and 2 more 255s. Okay, so each octet can be a 0 or it can be a 255. We also consider IP as a protocol in itself a best effort, connectionless, and unreliable. So you may be wondering at this point, hang on, if the internet uses IP, how do we have any form of reliability across the networks today? And the reason is because when we are talking about networking as a whole, we talk about reliability provided by upper layers. So let me give you an example of this. Let's say we had a particular host that connected to a routing segment, which connected to another router, and on the back of that, another host. Well, when the packets, we call them packets because we're talking about layer 3 of the OSI model. Remember, we call layer 3 of the OSI model packets. As the packets are leaving the router, let's say when it gets to this particular router, the buffer on the router is too full to accept a particular packet, so the packet essentially gets dropped. Now, IPv4 responsibility is not to let the originating host know that the packet was initially dropped, because it's not part of IPv4. IP will essentially allow that packet to be dropped for one reason or another, and what we would rely on essentially is when the rest of the packets reach the destination PC and the destination in PC pushes it up to the upper layer protocol, in this case TCP, the transmission control protocol, at layer 4, where it starts to use all these packets to rebuild these segments. Remember, we call the segments layer 4. When you use these packets to build the segment, you'll realize that it's unable to complete building that segment because some of the packets were not correctly received, because this particular packet was dropped. So TCP doesn't know where or how it dropped, but all TCP knows is I didn't receive all the packets I need to rebuild this segment. So what happens is this particular host here will ask this particular host up here to retransmit that packet. Hopefully that packet reaches the destination, and in turn the segment is able to be reconstructed, and TCP is then able to pass it to the application that needs that information. So when we think about IP as a protocol in itself, we consider it best effort, connectionless, and unreliable. But in order to have that reliability, we rely on the upper layer protocols to provide it. So when we say best effort, we mean IP essentially does its best to ensure that the packets are not dropped, but there's no way in actually ensuring through IP in itself that the packets are delivered. We say IP is connectionless, which means each packet is treated independently from all the others. So there's no sequencing sent from one computer, and there's no guaranteed dedicated path that one will take. So one packet might take a different path to another packet. And we also say it's unreliable. So we don't deliver the guarantee. The packet may be lost, it may be duplicated, or it may be delayed or delivered out of order. And that's where TCP comes back in to ensure that the delivery is successful and all the packets are received, so it can be rebuilt back into that segment. Okay, so the last point to pick up is what is an IP address actually used for, and it's used to represent you as an individual on the network. So for example, if we had, let's say, 3 PCs, each PC connected to, let's say, a particular network, which was split up by a couple of routers, and there was a PC over in the distance that needed to communicate with you, it would identify your network portion of the IP address to find which network you live on, and then it will use the host portion of the IP address to identify which PC or device you are inside that network. And later on, when we understand routing in more detail and how an IP address calculates the host and network portion, it will become a bit more clear. But essentially, an IP is normally a unique value that is assigned to you as an individual that allows other people to route towards in order to find you. Okay, so it's almost like your house address, for example. If you think about your street that you live in, your street would be your network, and what house you are on that street is considered your host part. So when it first came out, they came up with this idea of classful networking or classful addressing, and the idea around this was essentially they had a bunch of organizations and companies that needed to connect to the internet, and they all needed their own unique public IP spaces. So they had to find a way to essentially break up all the available IPs and give them out to companies. But every company had different requirements. Some companies and organizations were bigger than others, and some required more IPs than others. So they thought about splitting every IP that is available into particular groups, also known as classes. Today on the internet, A, B, and C is primarily given out to organizations that require public access. D is used for multicast, and E is used for experimental. Now the classes themselves, the way they work would be A is the biggest IP range, so they would go to very large organizations and companies. B would go to medium, and C would go to small. Now the other concept around classful networking was having the ability to essentially identify just from the first couple of bits of the IP address which class they belong to. So for example, I mentioned that an IP address is 32 bits of essentially ones and zeros, and depending on what patting of ones and zeros essentially depends on which which decimal number it equals. So to give you an example, they come up with this idea where if out those 32 bits it starts with a 0, so it doesn't matter what happens beyond this 0, so whether there's a bunch of 1s, 0s, whatever it is, long as it doesn't really matter about the next 31 bits, but as long as the first bit was a 0, then it would be considered a class A. The second, so for class B, the first bit had to be a 1 and the second bit had to be a 0, and the remaining 30 bits can be, again, any pattern, and that would identify class B. And each of these address groups had a pattern in the first octet, because remember, when we look about an IP address and we say, for example, like 192.168.0.1, this is one octet, this is another octet, another octet, another octet, the bit that identifies it is essentially the first octet. So the first octet started with a 0, or the first bit in the first octet started with a 0, and the 31 bits after that could be anything, then it'd be a class A. Same is true with the class B, long as the first 2 bits, so what we call the most significant bits in the first octet is 1 and 0, and the rest of the 30 bits are any pattern, we'd consider this a class B. And the reason they had this pattern in place was essentially routers, when they receive a particular IP address in binary, because again, remember, they see it in binary, we see it as decimal, they were able to look at the first couple of bits and quickly identify which class and in turn which network that belongs to. And this was an important time, as there was no subnet mask during the classful addressing. This came later with the introduction of CIDR, also known as classless inter-domain routing, which we'll get into a bit later in our video series. Classes are subdivided into 2 portions. You've got what's called the network address, and sometimes referred to as network bits, and the host address, sometimes referred to as host bits. So moving on from this, if we have a look at this table here that I've put together, you can see that I've got the classes, class A, B, C, D and E. We've got the identifying bits that were used to identify the classes, because like I said previously, there was no subnet mask during this classful stage of IP addressing, and this came out when CIDR notation came out. We've got these IP ranges. You can see, for example, if I gave you 10.1.1.1 or 175.16.4.3 or 195.195.2.7, we can have a look at what the first octet, and remember that's the only thing we're concerned about here in classful networking, which octet falls into which range, because that's the class that it lives in. So 10 falls in between 1 and 126, it's class A, 175 falls into class B, and 195 falls in class C. Now, throughout these ranges of IPs, there are some specially reserved IP ranges. So for example, 127 is referred to as a loopback address. If you wanted to test your own TCP IP stack, you would simply ping your loopback address. Alright, moving on to our next section, we're going to have a discussion around binary. Now, we said binary essentially is what our PCs see, whereas we would see it as decimal. So you can see here, I've got a decimal value, which is an IP address. It's split by the 4 octets, and then you can see beside it there's 32 bits, which is how our PCs or networking devices would interpret this IP address. So binary is a numbering scheme which allows only 2 possible values to exist, which is 0 and 1. The values are sometimes referred to as low and high or off and on. And because there's only 2 values, but in decimal we have up to 10 values, 0 to 9, we need a way to essentially put the 0 to 9 values, if you like, into only a possibility of 2 values. And to do that, we need some sort of conversion table. And to create that conversion table, what we're going to do is something very simple. We're actually going to start with the number 1, and we're going to double the number each time. So 1 doubled is 2, 2 doubled is 4, 4 doubled is 8, 16, 32, 64, and 128. Now notice what else I've done here is I've only done it 8 times. So 1, 2, 3, 4, 5, 6, 7, 8. Now I can go higher. In fact, I can go 9, which would be 256, 10, which would be 512, and then it go 1024, 2048, and all I'm doing is doubling the previous number. But because we're dealing with 8 bits, or in this case an octet, also referred to as a byte, we're only going to do it 8 times. So we're going to do it 8 placements. Now we have this conversion table together. We're going to use the conversion table to essentially put the decimal numbers into this table to identify where those decimal numbers sit. So, for example, the first number we have is 192. So what we're going to do is we're going to get the number 192, and we're going to ask ourselves, does 128 fit into 192? If the answer is yes, we're going to give it a 1. If the answer is no, we're going to give it a 0. In this case, 128 does fit into 192, so we're going to give it a 1. But what we've also done is we've used 128 now, so we're going to get a 192 number and we're going to take away 128, and that will leave us with 64. Because we've not yet reached 0, we're going to continue. So the next one would be 64, and the question is, does 64 fit into 64? The answer again is yes, so we're going to put a 1 there. So we take 64 and we take away 64 again, obviously that's 0. So because that's 0, all the others would in fact now become 0. Because there is no value left, there is no decimal numbers to put anywhere. So pretty straightforward. Now for the next number, which is 168, we're going to do the same again. The first question we need to ask ourselves is, can 128 fit into 168? The answer is yes, it can. If we then get 168 and we take away 128, we're left with 40. Does 64 fit in 40? The answer is no. Does 32 fit into 40? The answer is yes. And if we were to take away 32, we'll be left with 8. Can 16 go into 8? The answer is no. Can 8 go into 8? The answer is yes. And then we're left with all zeros at the end. So the outcome will be 1, 0, 1, 0, 1, 0, 0, 0. Now the next one is going to be even easier, which is a 0. So because it's a 0, they're all going to be 0. And the 1 on the end is all going to be zeros apart from the 1 here. So you're left with just the 1, and all of these bits are turned off. And all of these bits are turned off because of 0. And here we've turned on the 128, we've turned on 32, and we've turned on the 8. If you add them all up together, it equals 168. Here we've turned on the 128, and we've turned on the 64. If you add them both together, leaving all the others off, it equals 192. So that's how you calculate essentially a decimal number into binary. But how do you do binary into decimal? And the way we do that, let's say we get given a number. Let's say it's 1, 1, 1, 0, 1. So that's 1, 2, 3, 4, 5, 6, 7, 8. And we get asked, what is the decimal number that this binary value represents? What we can do is just simply place a 1 under the ones that are actually turned on. So we're going to turn on a 1. We're going to not turn on 2, not turn on 4, but we are going to turn on 8. We're not going to turn on 16, but we are going to turn on 32, 64, and 128. All we have to do now is add up the numbers that are initially turned on. So we've got to add 128 to 64, and then we've got to add 32 to that. So that would be 128 plus 64, which is 192, and then we're going to plus 32, which is 224. Then we're going to plus 8, which is 232, and then we're going plus 1, which is 233. So we know that the answer to this is actually 233. So the trick, essentially, to do anything between binary to decimal and decimal to binary is to understand about this conversion table, and then utilizing this conversion table we're able to move any number from decimal to binary and from binary to decimal. Okay, so now we've done the binary section, I want to go back to the discussion earlier where we had a brief overview of the identification bits used. As we previously mentioned, subnet masks are not used in classful networking, and I said that the beginning of the first couple of bits is used to identify the network. So you can see here, for example, 0 in the first bit of the first octet will identify that it's going to be a class A, and then providing it's still 0 on the first bit and all the ones turned on, it's going to be 127, 255, 255, 255. And the reason for that is because if we go back to our conversion table, so we had 1, 2, 4, 8, 16, 32, 64 and 128, and we took this number right here and essentially we translated that into decimal, so we had 128 turned off, 64, 32, 16, 8, 4, 2, 1 all turned on, and if we added 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, it actually equals 127. If you then look at the next range, you'll notice that it would be 1 will be turned on in the most significant bit in the first octet, but that's not enough to identify it because C, D and E also have 1 turned on. So the next bit to identify it is the 10. So we know, again looking at our conversion, that if we take a class B and we have a look, with the first bit being on, which is 128, and the rest being off, equals 128. The next one down, if 128 is on, 64 is off, but all of the others are turned on, that equals 192. So by doing this calculation and looking at the identification bits across the essentially the most significant bits in the first octet, a device, whether that's a router, a PC, whatever it may be, is able to identify which class of IP ranges that particular IP address lives in, and off the back of that it's also able to identify which portion of the IP is the network and host. What I mean by that is class A addressing, which is this guy here. The first octet is what's referred to as the network, and the last 3 octets are referred to as the host portion. Class B, 2 octets are referred to as the network, 2 octets are referred to as the host, and C, 3 octets are referred to as the network, and 1 is referred to as the host. This doesn't actually apply to D and E for now. This essentially allows us to be able to identify where the network portion stops and the host portion begins. So to sort of dive into that a bit more, let's just open up a quick whiteboard and we'll discuss it in a bit more detail. Okay, so to give an example of that, let's say we have a Ethernet segment, and off the back of this segment we have a few PCs connected to it. And our ISP has given us a class B range of 160, 60, 0, 0. Now the PCs will look at 160 in binary, and it will be able to use the network identification bits to realize that it's a class B address. And because it's a class B address, this means that we have the first 2 octets as network bits, and we have the last 2 octets as host bits. What it also means is no one else is allowed to use the 160.60 IP address. That's our IP address, and that's something that we're going to be using. Now we go ahead and give some IPs to the PC. We can give it 160, 60, 100 and 10. We can give this guy 160, 60, 90, 2, and 160, 60, 90, 3. Now, all these devices will be considered to be in the same network, and the reason they're in the same network is because long as the host portion matches on each device, it means that we can do anything with the last 2 octets. So we have the full range of up to 255 in these octets to assign to whoever we want. Now, because we've got the last 2 octets, we have a lot of variations that we can do. In fact, we have around or just above 65,000 available variations that we can do with these last 2 octets. And ultimately, that's most likely for my organization way too many IPs that I actually need. So you might be wondering, why don't the ISP then, instead of giving you a Class B, which gives you 65,000 IPs, give you a Class C? Because we know Class C uses only 3 octets as its network and 1 as its host. Therefore, you're cutting down on the variations of host you have, and therefore wasting less IPs. The problem with this is there's only 254 usable IPs inside that last octet, and because that last octet only has 254, normally that wasn't enough for the bigger companies. So the majority of the companies that were connected to the internet required at least a Class B. And this was one of the main drives to move away from this classful networking using Class A, B, C, D and E, and move to what we call nowadays a classless, where the subnet mask is put into consideration. Okay, so that's all we've got time for in this lesson. So I want to have a review of what we learned. We first of all had a discussion of what's to come in IPv4. We said this is going to be one of the largest topics and, in my opinion, one of the most complex topics to discuss in the CCENT journey. We said that we're going to have a discussion on classful addressing and classful networking, which is what we just done. We're then going to jump into understanding the future and the current, I should say, really not so much the future, but the current addressing scheme, where we would potentially use some sort of fixed length subnet mask, a variable length subnet mask, and what is CIDR, the classless interdomain routing, which is where classless comes into play, and also where we're going to learn a bit more of subnetting. And what we've done in the class today with the binary is to set that foundation of how we're going to get into subnetting later. We went into an IPv4 overview. We said that IPv4 is an unreliable protocol and it's best ever delivery, and it relies on the upper layer protocols like the transmission control protocol to do the error correcting, sequencing and retransmission of packets that didn't hit its destination. We then had a look of classful networks overview. So we had a look at the class A, Bs, C, D and E. We had a look at the identification bits that are used to identify what class it's in, and then on the back of that, how much of the IP address is a network / how much of it is the host address, because like I said, this was way before subnet mask is even being used. And then obviously we fitted in the binary overview. So we talked about that binary table where you had the 1, 2, 4, 8, 16, 32, 64 and 128. It doubled each time, and then depending on where you place the ones, essentially allows us to convert binary to decimal and decimal to binary. I hope this lesson has been informative. I'd like to thank you for viewing, and if it has been, please do like and subscribe.